Yeah, hello together. This is the 10th lecture within the series on 3D coordinate systems. And today I will present you a direct least square solution for the 3D similarity. First, we want to look what is meant if we say it's a direct solution. The first thing is we don't need any approximate values, which sometimes is difficult to get. One important factor is that direct solutions have a more or less fixed computing time if the size of the input data is given. This is very valuable if you have real-time applications. Now, under these conditions, there are many things which are allowed. So you can solve linear equation systems, you can find roots of polynomials, eigenvalues and eigenvectors of matrices, a singular value decomposition of a matrix, or you can find the minimum of a convex optimization problem, which is a very large range of routines which you can have within a direct solution. So the direct solution for the 3D similarity. We assume a simplified stochastical model. That means every point has an error circle, not an ellipse, so it's isotropic. The points are mutually independent, but the coordinates at each point have the same standard deviation in all directions. And if we use this direct solution, it has the advantage that it is optimal if this model actually holds, of course. And it's a very good approximation if there are no outliers in the data. We will show the solution for 2D and 3D similarities. There we see that the translation and scale estimation is identical for both. The rotation estimators are a little bit different, and I will go in both of them. We will have a look at the uncertainty of the results later when we discuss the maximum likelihood estimation using the same stochastical model. So let's start with the goal. The goal is starting from given pairs of corresponding points. So you have xi and xi prime. The number of points is capital I, and we assume that the dispersion matrix or covariance matrix of the measured points xi prime, the transformed points, is some standard deviation of that point, squared variance, multiplied with the unit matrix of size 2 or 3. We assume that the coordinate pairs are related by a similarity. That means a scaled rotation multiplied with the given coordinates plus translation gives the mean value for the observed entities. And the task is to estimate these parameters, lambda, r, and t, and provide the uncertainty, which we'll discuss later. Now, if this model is given for you and the xi are uncertain and the xi prime are given, then you just have to invert that model by solving it for xi. And if both are uncertain, things are a little bit more involving. There you need a different type of estimation model, namely the Gauss-Helmholtz model, which I will not discuss in this lecture. The main thing is now that we, in this specific case, under these conditions, we can use a different simplified model. Actually, we refer to the centroids of the observed coins. So you have a point cloud here and a point cloud here. You take the centroids and refer all coordinates to that centroid. So we have the observed coordinates plus the corrections minus the centroid of these coordinates is equal to the scaled rotation multiplied with the difference between the given coordinates and some unknown parameter u, which we don't know up to now. So the centroid for the given coordinates is nothing else than the weighted sum of the coordinates divided by the weights. So it's a weighted average of each of the coordinates. And we now have as unknown the rotation matrix, the scale parameter, the modified translation vector u, which is here, and of course the corrections. So this is our model. And now what we want to know, of course, is how this model relates to our original model. So the original model was just the given coordinates plus corrections is scaled, rotation multiplied with coordinates plus translation. And here we have the centroid of the given coordinates, of the observed coordinates subtracted, and here some unknown parameter u. So we have a relation between t and u. The lambda and r are the same. And if you rewrite this, you immediately see that the translation vector here is nothing else than the centroid of the observed coordinates minus lambda r u. So as soon as you have u, lambda and r, you can derive the translation vector in the original given model. We will use this equation later to look how this can be simplified. Now, what is the task? The task is to minimize the weighted sum of all the residuals. So we have here the residuals, which are in x and y, possibly z. And we have the weighted sum. And if you write that down, we have here the lambda rotation multiplied with the given coordinates minus the unknown parameter u minus the observed data minus the centroid transposed, and the same expression, and weighted, and the sum is taken over all points. So this is what we want to find, the minimum of this function with respect to the rotation, the u, the translation, and the scale parameter. We will start with the translation parameter. And before we do this, we rewrite this equation and just multiply the two expressions. So the first expression is this lambda r xi minus u, which appears here and there. So we obtain, taking the lambda out here, is lambda square multiplied with x minus u transposed, this transposed, multiplied with r transposed, which is this one, multiplied with r xi minus u. That's the first part. Then we have to take the mixed parts. That means the product of this expression and this term. So we get 2 times lambda. Then we have here the transposed of xi minus xc multiplied with r here in this case. And finally, we have the second part multiplied with the second part, which is just this expression, where you see these are the difference between the observed coordinates and the centroids. So this is a constant, so we don't have to take this into account. Now, how do we get the solution? We take as necessary condition the partial derivatives of this whole expression. So let's start with the translation. We take the partial derivatives of this weighted sum of residuals with respect to the translation parameter u. So the first part is this one. So we have here lambda square, and then we see here that here there's a unit matrix. So we just get lambda square multiplied with the sum of x minus u w. So this is this one. And then we take this part, which is minus 2 lambda. We have to take the derivative with respect to u, and we get the transposed of this one, which is nothing else than this expression. And that means we get 2 lambda square multiplied with the weighted sum of the differences of the given coordinates minus the translation parameter, which we don't know, weighted, minus 2 times lambda r transposed, and the sum of these equals 0. Now, what we know is that if these coordinates differences weighted sum up to 0, because we have here the sum of the weighted coordinates minus the sum of all the xg weighted, which is the same. So we have here a 0. And that means this expression needs to be 0, which means u will be the centroid of the xi, of the given coordinates. So this is a very important result, that the translation, which we didn't know up to now, actually is the centroid of the given coordinates, means it's the weighted sum of the coordinates divided by the sum of the weights. Observe, we can determine the centroid without knowing the numbering of the points. It's just the sum of the coordinates. And the second is, if we now plug in u equals xc into this equation on slide 6, we have here, then we see that if we solve for xc on the other side, so we get xc prime equals lambda art u plus t. That means the centroids fulfill our similarity. This is very important. That means if you have a centroid on the given side and on the observed side, the centroids actually transform into each other. They are, so to say, a fixed point of that similarity. So this was a translation. Now we can use this if we need. What we will do is now we take the scale parameter. A necessary condition is that the partial derivatives of our sum of residuals with respect to the scale parameter should be 0. Now what do we observe? We have here we have the lambda square, so the derivative is 2 lambda multiplied with this whole expression, and here we already have the lambda there, so we get minus 2 times this expression. So this is written down here, so we have here 2 times the second expression plus 2 lambda the first expression, and that should be 0. Now this is a linear equation for lambda. The 2 cancels out, and we directly can write down lambda as the sum, the weighted sum of the center coordinates of the observations multiplied with the rotation multiplied with the centered coordinates of the given coordinates, divided by this sum, which actually you see is because xi minus xc is the coordinate vector from the center to the point, and the transpose with itself is the squared length of it. So here stands the squared, or the sum of the weighted squares of the distances of the given coordinates to the centroid. Now the bad thing of this equation is it still has a rotation. So we cannot solve for lambda using this equation. Now there's a way out if we have small or negligible perturbations of our observations. That means, let's assume we have the noise of our observations is small, let's say below 1% or even better. Then we know that the rotation multiplied with the difference of the given coordinates with respect to the center is lambda power minus 1 multiplied with xi of the observations referring to the center. So if we now plug in r multiplied with this difference equals lambda power minus 1 multiplied with this difference, we can put this expression out. We are left with this part multiplied with the lambda, so the lambda goes on the other side, and what we get is the sum of the weighted squares of the distances of the observed points with respect to their center. So this is very plausible. So we have a point cloud here and a point cloud here. We take the centroids, we take all the distances here and here, we take the weighted sum of the distances left and right of the distance squared, and take the ratio and get our square of the scale factor. This is a very plausible result and very symmetric. We see it's an approximation because we have assumed that the observed coordinates are not perturbed too much, so the noise is not too large. But if you look at a direct solution, this is a very good solution already. So what is left is the estimation of the rotation. Here we use the centered coordinates. That means the given coordinates minus their center and the ich fange nochmal an. Okay, now we look at the estimation of the rotation. We use the centered coordinates. So we have here the observed coordinates diminished by their center, and the given coordinates diminished by their center. And we have here the centered coordinates. That means we have here the upper left index C for the centroid coordinate system. And now, what do we need to optimize? Let's have a look at our optimization function, which is, this one is not depending on R. This is the only expression which depends on R. So we have here the centered coordinates of the observed points, and here the coordinates of the centered coordinates of the given points, because U is the center of the given points. And now this expression has a minus sign here. That means if we have to minimize the sum of all the residuals, we have to maximize this expression of the sum. So this is exactly what happens here. So we need to maximize the sum of the centered coordinates of the given points multiplied with the rotation multiplied with the centered coordinates of the given points, under the constraint, of course, that R is a rotation matrix. Now, we come to the optimization function and we rewrite it. We use a classical result from linear algebra. That means the trace of a product AB is the same as the trace of the reverse product BA, if the matrices have this proper size. And we need it for rewriting this bilinear form. So this is a bilinear form. You have here a row vector multiplied with a matrix multiplied with a column vector. So we have this structure here. Now scalar and its trace is the same. So we have the trace of this matrix. And now we take A transpose B to be the first matrix A, and C to be the second matrix B, and we reverse it. So we put the C on the other side. That means this bilinear form is identical with the trace of this matrix. You see here C is a column vector, A is a row vector. So C A transpose is a product of which is a matrix. And this has to be multiplied with B. Now we apply this rule to our bilinear form and arrive at the trace of, we take the XIC on the left side. So we have here the dyadic product of XIC and XI prime C multiplied with the rotation matrix, multiplied with the weight. And now we perform the sum over all these expressions. And we get the trace of the sums of the dyadic products of our given and observed coordinates, weighted, multiplied with the rotation. We call this matrix H, which we can derive from our given data and the observed data. So what we have is a asymmetric D times D matrix. D is the dimension of our problem, 2 or 3. So we have here a 2 by 2 or 3 by 3 matrix, which is actually the dyadic products of the given and the observed coordinates, weighted. And if we put all these coordinates in a big matrix, a row matrix, D times I, and X prime for the observed coordinates, and W is a diagonal matrix with all the weights, we can write this as W X prime transposed. We will use this expression later. That means we need to maximize the trace of H multiplied with R under the condition that R is a rotation matrix. So this is our problem which we need to solve. And there are two different solutions, one in 2D, one in 3D. They differ to some extent. So let's start with 2D. So we write out the trace of the matrix H with R. So we have here the trace of H index XX, XY, YX, and YY. You see here this is the definition of this matrix, and we have the weights of the X coordinates, the weighted sum of the XY, the weighted sum of the YX, and the weighted sum of the YYs. And because the X primes and the X here are different, this is a asymmetric matrix. So we have to multiply this with the unknown rotation matrix. So if we do this, what happens? We take the trace. That means we have to take the first row multiplied with the first column, which is HXX cosine, which is cosine HXX, plus HXY multiplied with sine phi HXY. And then we have to multiply the second row with the second column, and we get here the minus sign multiplied with HYX, which is this part, and we get HYY multiplied with cosine, which is this part. So what you see here, we have the trace of this HR product of two by two matrices written down as a scalar product of the vector cosine phi, sine phi, which is a direction vector of our rotation, our unknown rotation, multiplied with a 2 vector where we know all the entries because we know the matrix H. So if the scalar product of H and R should be largest, then R needs to be parallel to H. That means cosine needs to be proportional to the first element and sine proportional to the second element. This gives us already the solution. So we have this vector H, which is this vector, with all these elements which we know. Then the rotation angle can actually be written as the arcus tangens with two arguments of h2 and h1, and we get phi as the optimal angle. So this is a very simple solution and very intuitive. Why is it intuitive? Imagine the following. You have here the coordinate system as the centroids of both coordinate systems at the same place. So you have here the coordinates xc and xc prime and yc and yc prime, and you have a point xi which is rotated to this point. So this is the unknown rotation angle. So let's put a coordinate system in the direction of x1, this blue coordinate system. What we need is a rotation, is a direction to this point. So this depends on the angle phi I in this case. And if we do this for all the points, we should be able to take the average of all these directions and get the optimal angle phi if we do proper weighting. Why is that so? So the hi, this vector, h here, in this coordinate system with respect to the point xi is nothing else than cosine sine phi I. And what is the angle? The rotation angle is the difference between the observed direction and the given direction. And now you see that we have here the cosine of the difference of two angles. So if we have the direction vectors of alpha, that means here this direction and this coordinate system, we have the cosine and the sine, and that means we get x times x, which is this one, plus y times y prime, weighted. So from this equation you can come to this expression in here, and the main thing is that we do a weighted sum over all these direction vectors for our unknown rotation. So this is a very plausible result, and is useful for direct programming. Now we go to 3D. In 3D, things are more complicated. There have been published at least 4 different solutions. You find a summarizing comparison by Eggert. There are 4 solutions. The first one with the singular value decompositions, the second with quaternions, the third one with orthonormal matrices, and the fourth one with dual quaternions, which are pairs of quaternions. I don't want to show all these solutions, but only the one with a singular value composition, because it turns out that this is the easiest way to accomplish. The proof is in the literature. So Aaron proposed with his colleagues in 1987 the following result. We take the matrix H. That means that's a 3 by 3 matrix. We make a singular value decomposition with an orthogonal matrix U and an orthogonal matrix V and a diagonal matrix S, which has only positive entries. Now, if we know that the mapping from the given coordinate system to the observed system is a proper rotation, there is no reflection, then the last element of V needs to change sign if the determinants of U, V prime have a negative sign. So, unless if there's already a proper rotation, we can also leave the 1 here, because then we will see the next slide that then the U and V will have the same sign. Now, if we have this singular value position in US V transposed, we just multiply V with the transposed of U and get our optimal R. This is very interesting because it's an extremely short algorithm. We build up the H. So H is nothing else than this expression. We make the SVD and we multiply these 2 matrices. So this is an extremely short and efficient algorithm, and it has very nice properties. The first thing is, if all the singular values are distinct, then the result is unique. That's good. If the determinant of H is positive, and we will prove this immediately, we obtain a proper rotation matrix R. If the determinant is negative, we have a reflection. That means the determinant of R is -1. That means we have an orthogonal matrix R. And if the determinant is 0, the points are coplanar, and we have to make a special discussion, which I don't want to follow. Now, how is that with the determinant? Now, let's take any triple of points in the given coordinate system and in the transformed system. We have the matrix X prime, which is a 3 by 3 matrix, is the rotation matrix, which is a 3 by 3, and X also is a 3 by 3 matrix. If we now take determinants, the determinant of X prime is equal to the determinant of R and the determinant of X. So, the determinant of R now indicates whether we have a reflection or no reflection. If it's positive, we have no reflection. If it is negative, we have a reflection. Now, actually H is the product of X multiplied with W and X prime transposed. So W is positive, so the sign of H, the sign of the determinant of H is the same as the sign of the determinant of X multiplied with the sign of X prime. So if we actually have a transformation of these 3 points into these, we have a reflection, then X and X prime will have determinants of different sign. That means H will have a negative determinant. And that means we come to the following result. I have a shorthand notation for the sign of the determinant as D. So SD of the rotation, the sign of the determinant of the rotation, is from this equation the sign of the matrix X multiplied with the sign of the matrix X prime. Now this is exactly the same as the sign of the matrix H. And this is the sign of the matrix UV transposed, because we have SVD and the S has positive values. And actually, if we transpose this matrix, we get V times U transposed. We have the sign of the estimated rotation. That means the sign of the given rotation and the sign of the determinant of the estimated rotations is the same, and it's either positive or negative, because we have assumed that these are non-coplanar points. So we see this is a very nice result, and only in the case that we have noisy data and we have a no reflection and the noise of the data causes a negative sign for the determinant of H, then we have a problem. But this is not a problem in the mathematics, but it's a problem with our measurements. So what have we found? We have found direct solutions for the similarity. We use the simplified stochastical model. That means each point has isotropic uncertainty and all the points have different weights. They are mutually independent. When we have seen that we have direct solutions in 2D and 3D, they are optimal if the model holds. That means we already have a good solution. We have to think about the scale estimate. If the noise is not too large, the differences will not be very large. And of course, these direct solutions are good approximations if we have more complicated stochastical model and if there are no outliers. And what we will discuss later is that we get the uncertainty from the maximum likelihood estimation, of course, with the same model or with the model which we then apply for the optimal estimation. So this is the lecture for today. The next lecture will be on the maximum likelihood solution for the spatial similarity. See you then.